So my talk is going to be almost in a certain sense a two-part talk, because the first maybe a quarter, 30% of my talk will be about our ongoing experiments on cold atomic gases, where we're asking the question of how does dissipation or active measurement and feedback allow us to generate or create new kinds of quantum states that are intrinsically out of equilibrium but might not occur normally in nature. And the second half of... Sure.
The mic doesn't do anything other than record.
Should I just shout?
For volume, you're just going to have to speak loud.
Okay, I'll just shout. All right. So the second half of my talk is more about the kinds of systems that are indicated in a schematic here, where we use optomechanical systems of various kinds in conjunction with cold atomic gases and optics to generate various kinds of feedback. And what I want to show you is that the very nature of measurement and feedback can actually create out of equilibrium states with very, very interesting properties that in some ways depart from our traditional understanding of equilibrium phase transitions and Landau-Ginzburg-like phenomenology. Okay, so just to kind of set the language and the kind of terminology straight, so we, on the one hand, we really like working with cold atomic systems because they're highly isolated, they have very, very long coherence times, and they can exhibit various kinds of quantum behavior over very, very long periods of time. And there's been increasing interest in saying these systems are so isolated, how is it possible for them to actually equilibrate or thermalize? How do they find equilibrium? And our understanding of how these systems, albeit highly constrained, because of conservation laws and so on, how do they actually find equilibrium? And that there's been an increasing understanding in this regard. On the other hand, we also know about classical thermodynamic systems, which we always kind of consider to be in some kind of an equilibrium or steady state behavior. And we understand their phase transitions and so on through various kinds of phenomenological theories. Somewhere in between are these open quantum systems, which are really coming to the fore in various physical manifestations, where the timescales or the interaction of intrinsic or coherent interactions is commensurate with the timescales of dissipation. And now the question is, if the intrinsic timescales are commensurate with the rate of coupling to the environment, these systems are in a certain sense always out of equilibrium. And nonetheless, even if they're out of equilibrium, they can exhibit various kinds of dynamical steady state phases, which arise from this interplay between quantum coherence and dissipation. And so what is the new physics that such systems, such open quantum systems, can manifest? And in particular, the kinds of questions we are asking is, can we really kind of develop some kind of a microscopic or bottom-up picture of thermodynamics and decoherence, quantum measurement, and quantum to classical transitions by looking at the precise effects of fluctuations and dissipation? What happens to these phase transitions, for instance, if we choose to violate the fluctuation dissipation theorem or other kinds of effects that we normally take for granted in macroscopic thermodynamic systems?
I have an objection already.
Sure. That was fast.
Using classical thermodynamics, the interaction strength between the system and the environment is very strong. It's actually just the opposite. The vanishing is weak.
Sure. Okay, I understand what you're saying, and the in a certain sense, I'm talking about the single particle. I'm distinguishing single particle interactions versus the collective interactions in this graph. So it might appear a little misleading because I understand what you're saying. You're basically saying that for a macroscopic thermodynamic system to exhibit long-range order or any kind of a phase, I really want G to be very, very large to overwhelm the dissipation.
So gamma is vanishing explore. Doesn't matter. That actually belongs to open system.
Okay.
Go on.
Okay. So in terms of the physical systems, I want to talk about, on the one hand, how do we actually get to this regime where of commensurate interactions? Cold atom systems, like I said, the rate of dissipation is actually very, very small. So I'll talk a bit about how we can introduce tunable dissipation via this what I call a non-destructive measurement technique, and move this kind of isolated system to this kind of an open quantum system regime. And the second part of my talk, I will discuss how we come the other way around by taking these macroscopic optomechanical devices and try to isolate them better and better and better from the environment, reduce the dissipation, and then move them to a point where they exhibit new behavior on account of the reduced dissipation and peak measurement. Okay, that's a picture of one of our labs where this happens. So the first part, how do we actually measure and control ultra-cold optical gases through measurement? These gases are so cold that we typically think of measurement as the very end of a long process of creating a quantum coherent state and studying it. And we kind of assume that as soon as we take an image of these gases, we typically destroy them because the rate or the amount of energy we impart to the gas just by the act of imaging them or shining light on them is actually enough to destroy the condensate. So we came up with this technique of imaging optical lattice gases in such a way that the act of imaging also restores the gas continually to its ground state. And the way it does this is to, if you were to think of these atoms in some kind of an optical lattice, cool down to the lowest vibrational band. And we can actually use coherent two-photon transitions to basically cycle the atoms between this triplet of vibrational states using the spin degree of freedom. And that last process is an optical pumping step which emits a photon. So if we were to repeat this again, every time the atom emits a photon, it comes back into the ground state. Okay? So we can cycle this process at varying rates, and these are various fluorescence images of this optical lattice gas. As you can see, as we cycle this process at a rate that is more and more rapid, we can extract more and more fluorescence from each atom, and this is the same kind of ultra-cold gas at varying rates of measurement. So the gamma m is just the rate at which we cycle this process. Okay? But we know that every time we get a fluorescent photon out, the atom ends up in the state that it started out with. Okay? So now the question we were asking is, well, we are clearly this atom is emitting spontaneous photons. Clearly, the act of emitting a spontaneous photon is a projective measurement. What is the back action of this projective measurement, and how does that impact the optical lattice dynamics? And the way we chose to measure it, these experiments were done in our lab, which does not yet have a single site resolution. So we have to have some way of understanding or quantifying what is the rate of tunneling or what is the lattice dynamics. And the way we chose to do this is just by using photo association. The fact that if we have two atoms on a single lattice site and one of them is in the excited state, then such pairs can very rapidly photo associate by the presence of a photon, and they can be lost from the trap. Okay? So just by quantifying the rate of loss and distinguishing between single particle loss, which just happens because of background losses, versus two-body loss, which are these kinds of coincidence occurrences, we can basically quantify the effective tunneling rate of the atoms as a function of the two-photon loss rate, kappa. Okay. And so now you might normally, kind of the classical intuition here would be to say, well, look, I'm trying to measure or measure the positions of these atoms, and I do so by shining light on the atoms. But of course, the presence of light also causes photoassociation. So the more light I shine on the atoms, the more I get the atoms to fluoresce, the faster the atoms are going to decay because of two-body loss. So the classical intuition here would be to say, as I increase the measurement rate, I'm going to decrease the two-body photoassociation lifetime. In actuality, what actually happens is the experiment shows that we get the opposite trend, that as the atoms fluoresce more and more and more strongly, the photoassociation rate, instead of going up, actually reduces. So the more the atoms emit fluorescence, the longer the atoms, or the longer the two-body lifetime of the gas. And the reason for this, of course, is that the classical intuition here is strong because at very, very small rates of measurement compared to the tunneling rate, the atoms more or less usually undergo spontaneous, usually kind of undergo coherent quantum walks in the lattice. But as we measure the atoms, or we cause the atoms to emit spontaneous photons at a rate that is very large compared to the tunneling rate, the atoms are repeatedly projectively measured and projected back into their lattice sites. So the tunneling rate in the presence of rapid measurement is actually much, much smaller than the bare tunneling rate. So the atoms essentially never go anywhere because they're being repeatedly projectively measured, and they are localized into each lattice sites. Okay? And this is basically what is known as the quantum Zeno effect, that the presence of repeated measurements or repeated projective measurements essentially freezes the evolution of the lattice gas. And the increased two-body lifetime is basically a manifestation of that quantum Zeno effect. And we can go all the way from the very, very strong measurement limit to the weak measurement limit, where we see this very, very clear transition from a regime where the measurement has no effect on the tunneling to a regime where the tunneling is strongly suppressed by the act of measurement.
Now, you presented in terms of giving that rate, that is the projected measurement rate in inverse seconds. If I put on here what the tunneling rate is,
yeah,
then, okay, up there.
Yeah.
So, is that what you expect?
I'll show you. Yeah, it turns out it's actually very close to what we expect. So yeah, if we took this data, and then we can also do right now single particle Monte Carlo simulations, which and I can show you. Here are a couple of trajectories of these atoms. As you know, that if I have just a single atom and I let it evolve coherently in an optical lattice, what I expect to see is that the wave function grows as basically as a Bessel function. So you expect to see this linear growth of the wave function of a single atom in an optical lattice from coherent quantum walks. And every once in a while, the atom emits a photon, causing it to localize. So you see this fan, and every once in a while, you see that the atom kind of sporadically and spontaneously localizes to a lattice site and then starts evolving again. And so this kind of a sporadic localization, it would be in this regime where most of the time the atoms are evolving coherently. In contrast, as I now turn up the measurement rate to a point where it is actually much, much larger than the tunneling rate, what you see is that the atoms are localized more often than not. And this behavior is actually a very classical stochastic diffusion, which ends up in this regime. And so if I were to quantify the rate of transport or the rate at which the atoms or the wave function grows as a function of time, classically we expect this exponent alpha to be 1/2. And quantum mechanically, we expect this coefficient alpha or the exponent alpha to be 1. And we see this transition, and if you were to kind of put some kind of distinguish this behavior from this behavior, it happens somewhere around gamma over j of 0.1 to 0.2, which is pretty close to what we see here. Okay.
So using the word strong and weak in here by the rate of measurement.
Rate of measurement in comparison to the Baire tunneling rate. That's right.
And the more frequently you measure, it becomes more classical, right?
Exactly. Exactly. Okay. Of course, these are all the data that I have been presenting was in the very low filling fraction limit, where you could essentially ignore the fact that there are multiple atoms in this lattice gas. Or experiments that we are doing right now is to say what happens if we now increase the filling fraction of this lattice, and what is the role of many-body interactions and indistinguishability on this kind of a transition. Okay. Or at first glance, you would say, well, you have a quantum system, and then you couple it to some kind of spontaneous, or you cause it to emit repeated spontaneous photons, and so the gas became classical. That's common sense. You would not expect anything else. That you have an isolated quantum system and you couple it to an environment more and more strongly, it becomes classical. Okay? So then you would say, well, this is kind of to be expected. Of course, there is this, you expect to see a transition of some kind. Whether this is a transition or a crossover, we can go into those details. But this is kind of what you expect. The other question one can ask is, in this intermediate regime, are there states or kinds of many-body behavior that would not occur either in this regime or in that regime? Is there something new that comes about in this intermediate regime where gamma and j are commensurate?
Can I push that a little bit further? That is, can you go into the non-Markovian regime? Because quantum trajectory.
That's the entirety of my second half of my talk.
And you probe into that. Correct?
Yes, though in a slightly different system, okay. But I will show you exactly. Okay, so I'll give you a couple of examples. These are ongoing experiments in this regime. The previous experiments I told you about the quantum Zeno effect, the measurement was essentially uniform across the lattice gas. Okay, we had one scattering rate or one gamma. Gamma was essentially independent of space. And if we now instead make gamma the measurement rate a strong function of space by, for instance, measuring very, very strongly in one region of the lattice gas versus in another, what you can convince yourself is that atoms atoms in regions of weak measurement actually essentially tunnel freely, or in a coherent sense, like I showed before. But atoms just within this region are very strongly projected or projectively measured and localized. So the net effect of this kind of a spatially dependent measurement strength is for the atoms to exhibit or a one-way flow into this region of strong measurement. Okay? This is essentially what in cold atom physics you would call entropy segregation. You're basically increasing the filling fraction in this region. And remember that our imaging technique preserves the atoms in the lowest ground state or the lowest vibrational band. So this is a way in which you can take a lattice gas at very low filling fraction and decrease the entropy in this region at the expense of the entropy in the surrounding regions. Yeah?
So are you saying that your quantum xenophysics is somehow one way, which is a little surprising? I would have thought that it would be.
It's a little subtle. So these experiments, we can discuss this more offline, but these experiments use two quantum Zeno effects. One is the measurement quantum Zeno effect, but the other is the fact that the atoms, once they are in the region of strong strong measurement, they also tend to avoid each other because there is also a photoassociative or a dissipative loss effect because of photoassociation loss. So because of those two effects, there's a one-way process.
I'm imagining maybe the question is more simple. If I've understood correctly, what happens is that in the part of the lattice where you're not making measurements, things are relatively free to diffuse. But when they get into the place where you are making measurements, they're frozen.
Mm-hmm.
And so you tend to collect things in the place where they're frozen.
That's
what's
sure.
going on.
But I think Alexei's question was, if everything is time reversal symmetric, then how do you ever end up with one-way process? Or how do you ever end up with one-way flow? That's your question, right?
Well, my question was if the site is empty and you're measuring it, you don't want to go in there.
Very good.
The same way in which if the atom says here, it doesn't want to leave.
Very good. Very good. Yeah. Yeah.
But
Yeah.
I think you've answered it.
Okay. So to maybe give you a better idea of so if I had so this is to further answer the question, why does this happen, or what is this due to, this one-way flow due to? If I had the optical lattice and superimposed a tilt or a gradient on it, now we know that in the completely quantum coherent regime, the atom is not going to go anywhere. It's just going to exhibit Bloch oscillations. Okay. Now, in the opposite regime, in the regime of very, very strong measurement, again, we know that the atom is not going to go anywhere because it's periodically projected back into the same lattice site. But in between, when the measurement rate and the period of Bloch oscillations or the Bloch oscillation frequency is commensurate, the atom can progressively lose energy by running downhill. And so here we have a localization because of quantum coherence. Here we have a localization because of rapid projective measurement. And somewhere in between, we actually have a phase that exhibits directed percolation. Okay? And this exhibits all the characteristics of a metallic phase in this Bose gas, but a metallic phase because of this commensurate rate of measurement and intrinsic tunneling. Okay? And whether this is a phase transition or a crossover is something that we are still experimentally studying. Okay?
Sorry,
Yeah.
So why is the insulating phase strictly insulating? If you have infinitesimal dissipation, I would expect there to be weak conduction from higher order processes.
In this regime?
Yeah.
Which higher order processes?
No, I mean, you can eventually dump the bath. You have some weak coupling to the bath, so you can.
Okay, so
so infinitesimal coupling should destroy. Probably produce exponentially weak conduction, but still something.
So those the background loss rates or those kinds of infinitesimal kind of light scattering and so on, that would kind of blur this further down this way. But those in these calculations and simulations, we've ignored those things. Okay. So now I want to kind of shift gears a bit and also get to this question of what does the role of the environment have to do with these kinds of driven dissipative or non-equilibrium phase transitions, non-equilibrium states of matter, and also like the previous question of, well, what exactly can we, if we modify the correlations or the nature of the environment from Markovian to non-Markovian, are there new states of matter or new kinds of phase transitions or new kinds of critical behavior that comes about because of the fact that the environment now has some kind of a memory or some kind of a non-Markovian characteristics. So, sorry, go back one step. So these kinds of experiments are not cold atom experiments. These experiments involve macroscopic resonators of various kinds and the interaction of these resonators with optics. So these so-called optomechanical systems. And the ingredients of this optomechanical systems, there are a few ingredients. The first is very, very high quality mechanical resonators. The resonators that we are working with and the resonators that I will show you kind of look like this. It looks like the hole in a silicon substrate, but this is actually a very, very thin silicon nitride membrane. Now this membrane, I tell my students it's almost as good as a rubidium atom because its quality factor is on the order of 100 million. Okay? But it is a lousy rubidium atom because every day you walk in, the resonance frequency is slightly different. In fact, the quality factors of these resonators are so good that if the lab temperature changes by 1 microkelvin, the resonator frequency changes by a few line widths. So to do these kinds of experiments, we had to implement kind of rather accurate feedback techniques to stabilize these systems. Okay? And these kinds of this structure out here is to further shield the resonator from external sources of dissipation by implementing basically a phonon shield that prevents the energy of this resonator from being dumped into the environment. Okay? Basically, this prevents propagating modes of the substrate from removing energy from the resonator. Okay, so that's the first ingredient. We have a very nice mechanical resonator. The second ingredient is we embed this in a cavity, a Fabry-Perot cavity, so that we can use the optical radiation pressure to impart various kinds of control on this resonator. And the third ingredient is, of course, that we can couple this optomechanical cavity to a cold atomic gas, which lives in another vacuum chamber about a couple of meters away in the same lab. And the way this works is that as we shine light into this cavity, the motion of this membrane is imprinted onto the phase and amplitude fluctuations of the transmitted light. And that light can then induce electromagnetically induced transparency in this atomic gas. Basically, what that means is that the light can mediate a coherent quantum conversion between the phonons of this resonator and the magnons or the spin waves of the cold atomic gas. And we can, of course, that's a reversible coupling. So we essentially have a magnon or a phonon to magnon interaction. Okay? And here's an example of that the motion of this resonator induces an EIT in this cold gas. And the nice thing about this is that now the cold gas, or indeed any kind of these quantum spins, can mediate a effective optomechanical interaction or can dress the optomechanical interaction that the membrane actually essentially sees. Okay. The other nice, neat thing we found was that we initially built these kinds of phononic bandgap structures to improve the quality factor, but we also realized that this kind of the localized modes of this substrate can mediate interactions between discrete mechanical modes. Now, this membrane is like a trampoline. It has many, many different modes, and these modes can be coupled by some interaction or by some excitation of the substrate. Now, the substrate, of course, is a very lossy structure, so this line width is very large. But for various under various circumstances, the substrate excitation at this pump frequency omega s can couple two discrete membrane modes omega I and omega j. And now you can probably recognize this very much as just a mechanical equivalent of an optical parametric oscillator. So you have a signal and idler, which are these two very high Q modes, and they can be coupled by this substrate excitation, which we call the omega pump. And as you know, optical parametric oscillators or optical parametric amplifiers like this can exhibit very large degrees of two-mode squeezing. Now, in the optical domain, you kind of think of this optical parametric oscillators as having squeezing of about 3 dB. There is a 3 dB limit to optical parametric oscillators. Of course, that is in the steady state. And in the optical domain, you kind of think of the steady state as being attained in nanoseconds or sub-nanosecond timescales. Of course, these mechanical resonators have a mechanical ring down time of a few minutes. So there's a very, very large period of transient dynamics where we can actually extend the squeezing all the way up to like 17 to 20 dB. and this is the Hamiltonian that creates this kind of a two-mode squeezing. And this is also very, very similar to, in cold atom language, this is actually very similar to the kind of Hamiltonians that one sees in spinor condensates as well. Okay. So now the question I want to ask is, with these kinds of tools, so we have very high Q resonators. We can dress those resonators with an optomechanical interaction involving cold atoms, and we can also create these kinds of mechanical parametric amplifiers. Can we now study various kinds of phase transitions, making use of the fact that in this system we have a very, very long transient time scale, and this we can measure, we can impart weak measurement and feedback to the system. So these kinds of, in this intermediate regime, these open quantum systems, even though they are intrinsically out of equilibrium, they still exhibit what you can loosely call a phase transition, meaning a transition between different dynamical steady states. And that being said, how do you actually define a phase transition in this intermediate regime? In the classical regime, we can write down a free energy because the system is in equilibrium and identify critical points or phase transitions by singularities in the free energy. In the quantum case, we can write down a Schrödinger's equation and identify critical points as a vanishing energy gap. Here, in this open quantum system, the system is always out of equilibrium, so we can't write down either a free energy or Schrödinger's equation. We have to write down, in regimes where it is applicable, we can write down some kind of a mastery equation with this Lindblad operator here, and in regimes where it is applicable, we can write down an effective non-Hermitian Hamiltonian that looks like this. And now we can identify criticality or critical points by looking at vanishing spectral gaps of this complex or a non-Hermitian Hamiltonian. Okay? So depending on the system, the definition of criticality or the definition of a phase transition is rather maybe schizophrenic, so which opens a broader question of what properties or what aspects of criticality here are common to what we recognize as critical points or critical behavior in these two different systems. Yeah.
But the middle one, I mean, that relies on the Markovian approximation.
Yes, that's why I said in regimes where it is applicable.
But it's never precisely applicable.
Sure, it's a question of time. It's a question of time. It's a question of time scales.
Okay, because the left and the right are precise.
Yes. Yeah. Okay. So the question I want to answer in the remaining time are, can we use these kinds of hybrid quantum systems to create very interesting dynamical many-body states and dissipative phase transitions? The answer would be yes. For those of you who want to tune out, I'll just give you the punchline. Can we find new routes to quantum state preparation by weak measurement, feedback, and controlled dissipation? The answer is yes. And what is the role of the environment on the critical behavior, and can criticality be modified by non-equilibrium reservoirs or by non-Markovian environments? And lastly, can we create novel kinds of dynamical phases purely by modifying the nature of the environment? Now, this is something that you might think of as being unique to open quantum systems, because if I look at, in either an isolated quantum system or a classical thermodynamic system, if I give you the system Hamiltonian, usually that is sufficient for you to extract the phase diagram of the system. And what I'll try to show you is that in these open quantum systems, I can give you the same system Hamiltonian, but show you that the phase diagram actually depends on the nature of the environment. Okay, so
you also need to see that in the middle case, that the system reaches some
steady state. Yes,
right?
yes.
Otherwise, there's no sort of
Of
phase,
course, yes,
right,
yes, yes.
to begin with.
Yeah.
And in that sense, you would tell us how fast the development, the evolution.
Yes, I will. Yep, yeah. Okay. So just to kind of get the language again straight, this is my toy Hamiltonian. It's a very minimal model of a phase transition, and it's basically just this parametric oscillator Hamiltonian I wrote before. But in order for me to establish a steady state, I also have to include two additional effects. One is pump depletion and nonlinear damping. Okay? If I include these two, then I can write down this Hamiltonian as essentially a 5-4 model that looks like this. And the important parameters here are are mu, which I call the strength of the drive. So remember the model, I have a pump frequency, which I'm driving the system at some pump frequency, and this pump can mediate the down conversion of a pump excitation into two discrete excitations. One I call the signal, one I call the idler. Okay? So basically, I have one excitation at one frequency dividing into two excitations at two lower frequencies. So now you say, if I now increase the amplitude of my pump drive, initially my signal and idler beams, or signal and idler excitations, are just characterized by their thermal or vacuum excitations. So they're down here, and for very, very weak pump amplitudes, my energy landscape essentially looks like that. But beyond a certain strength of my pump amplitude, the rate of down conversion is going to exceed the intrinsic dissipation. So now these signal and idler excitations are going to reach some kind of a dynamical steady state. Okay? And this is now the energy landscape looks like this, and this ball is going to roll downhill, breaking a symmetry. And the symmetry in question is the phase difference between the signal and the idler beam. And that this phase difference is spontaneously chosen. So this transition breaks a symmetry, which is the U1 symmetry associated with this angle. Okay? So for very weak pump drives, I have no excitations, or essentially the signal and idler beams are at the vacuum level or the thermal excitation level. Beyond a certain amplitude, they are at some steady state given by a spontaneously broken angle between the two. Okay? Essentially that's my phase diagram. This is as simple as it gets. So just to kind of associate this picture with a few different systems, this phase diagram, or this kind of a Hamiltonian, describes optical parametric oscillators, like I said before, where a pump signal can create excitations at the signal and idler frequencies. The time scales of equilibration are on the order of nanoseconds or smaller. This is also associated with what is known as the open Dickey model, where atoms inside a cavity which are being pumped can, beyond a certain point, scatter photons into the cavity and establishing a steady state amplitude of light within the cavity. At the same time, they also exhibit spontaneous order. Here I have the pump and the signal and idler beams. There is a optical excitation as well as the spontaneous the excitations created by the spontaneous order, which are the phonons in this lattice gas. So here I have excitations of highly differing magnitudes. One is an optical excitation with a damping rate on the order of microseconds. The other is the phonons in the spontaneously formed lattice gas with a damping rate on the order of milliseconds. And lastly, the experiments I will show you, which is an optomechanical system where the signal and idler beams or the signal and idler excitations are modes of this membrane with damping times on the order of seconds. Okay. So in terms of talking in terms of phase transitions, one likes to take, the question was, do these exhibit some kind of a steady state? And these are the steady state measurements of this phase transition. And as you can see, this is the growth of order beyond a certain strength of the drive. Mu is now the strength of the drive and it's normalized such that the critical point occurs at mu equals 1. And you can see that below mu equals 1, the signal and the idler excitations essentially are at their vacuum levels or thermal excitation levels, and then they grow, establishing a steady state. And we can associate an exponent with the rate of growth of the ordered phase, beta. At the same critical point, we can also measure the susceptibilities of the signal and idler excitations, and we see that diverges. We can associate that with a critical exponent called gamma. And we can also look at the relaxation time of the system near the critical point, and we can see that the relaxation rate also diverges. We can associate that with the exponents nu z. And you can see that if we were to take based on these steady state measurements, these are exponents that you would typically associate basically with exactly the mean field expectations. Okay?
Yeah. Just a few years ago, I'm sure you know Vengalattore,
Yeah.
and DOE at all. I wonder how your work compares with theirs.
In some senses, at the level that I've talked to you about right so far, it's actually very close. Very close, but I'll show you how we actually, in the remaining part of my talk, I'll show you how we go beyond that. Yeah. There's also, in some ways, we very accurately confirm their predictions. I'll get to that in a second. I'll let you know when I do, but then we go beyond that slightly as well. Okay, so you would look at this and say, this is probably the most boring phase transition one can study. There's two modes. There's mean field behavior. You measure the dynamical steady states, and you have verified mean field predictions. There's no surprises here, okay? Which is a great starting point. Okay. Now, how do we, the way we actually want to go beyond this is to say this is an open quantum system, and we actually want to study the effect of the environment on criticality. And the way we decided to do this is to actually use a paradigm called the Kibble-Zurek paradigm, okay, which cold atom people know very, very well. Basically, the essence of this paradigm is to realize that near a phase transition, at least an equilibrium phase transition, there are a couple of parameters that diverge: the relaxation time and the correlation length, okay, and they're associated with their own exponents. And the point is, near the critical point, because of either the vanishing energy gap or the divergent relaxation time, if I were to cross from the disordered phase into the ordered phase, but do so at a finite rate, then very close to the critical point, the system can never keep up with my changing Hamiltonian. So the system loses track of the change of my changing Hamiltonian because the relaxation time is diverging. So where does that leave us? That gives us, or Kibble and Zurek came up with a very elegant and rather universal way of understanding the behavior of a system as it is driven through a critical point at a finite rate. And based on their paradigm, it turns out, and I'll explain why in a second, but it turns out that one can use such quenches or rapid changes of Hamiltonian from the disordered phase into the ordered phase and look at the system once it is in the ordered phase to extract various aspects of the critical point. So this sounds rather counterintuitive. What I'm saying, or what they are saying, is you can do a highly non-equilibrium experiment and extract equilibrium critical points using these kinds of protocols. And why is that the case? Let's imagine that the system is initially deep in its disordered phase. And what I have plotted here is the relaxation time, which, as I told you, diverges near the critical point. So very, very far away from the critical point, everything's fine. If I were to change the Hamiltonian slightly around here, the relaxation time is so small that the system is always going to be, in a certain sense, adiabatic. Now, if I very quickly go from here into the ordered phase over there, but do so in a very, very fast rate, then the system can't keep up because in this period here, the system cannot be adiabatic. The relaxation time is too large compared to the rate at which I've changed the Hamiltonian. Which means that even though deep in the ordered state, we expect to see some kind of a homogeneous ordered phase, in any finite rate quench, this will never happen. What I will see is that the system gets frozen in the vicinity of the critical point. And by the time it comes out here, it has to recover in a rather rapid way. Okay? And so what that actually causes is that instead of having a homogeneous phase, what you actually see is domains. Okay? Another way of thinking about it is because the relaxation time has diverged, although the system needs to break a symmetry, different regions of a spatially extended system cannot communicate that choice of the broken symmetry instantaneously. There is some kind of a bound on the speed of excitation, speed of light, or speed of sound, which means the broken symmetry can only be communicated locally, causing domains. Now, the faster I go from here to there, the smaller the domain size. If I go very, 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 very slowly, in principle, the domain size should diverge and become larger and larger, but it can never become as large as the system. So just by looking at the number of domains or the excitations created as a function of the quench rate, I can establish certain scaling laws. And here's the key part of the Kibble-Zurek paradigm. The exponents of these scaling laws depend on the critical exponents of the transition. So just by going very quickly from here to there and looking at the rate of or the excitation density or the number of domains and so on, I can extract the critical exponents. Okay? And this has been demonstrated, essentially, I would say, as in a range of physical systems as large as it gets, all the way from single qubits to potentially the early universe. Okay? But the system that I'm talking about is, like we said, a minimal realization of a phase transition. It has no topological defects. It has no spatial extent. But Kibble-Zurek scaling is about more than just topological defects. It basically just is a measure of the non-adiabaticity of the system near the critical point. So I could choose to apply the scaling not just to topological defects, but to any measure of non-adiabatic behavior, such as excess heat or a dynamical hysteresis. Okay? So what in the system that I want to talk about, or the optomechanical system, what happens is that if we drive the system from the disordered phase very quickly past the critical point, the system initially will not respond. Even though it's supposed to adopt a finite amplitude, it cannot respond because it is frozen out. And at some point, it realizes that it is deep in the ordered phase and responds by exponentially growing its amplitudes, what we call inflation, and reaches its dynamical steady state. Now, if I were to now go back, meaning reduce the amplitude of the drive, the path taken by the system is very different. Okay? So this kind of a dynamical hysteretic behavior is also a measure of the non-adiabatic behavior, and so I can extract the freeze-out time and the dynamical hysteresis area and relate that to the critical exponents of the phase transition in this manner. And doing these kinds of experiments, what we can see is that we do indeed extract the critical exponents that I had measured based on my dynamical steady state measurements. And these Kibble-Zurek-like protocols show this kind of a scaling, and they agree very, very closely with my previous measurements of the dynamical steady state. Okay? So far, so good. Now here comes the crux. I'll ignore that. Because these membranes are so well isolated from the environment, we can actually pretend that the intrinsic Markovian environment is not there, and we can actually use weak measurements and feedback to impart our own dissipation and our own Langevin forces. Okay? So we can basically fool the system into thinking that it is embedded in an environment which is distinct from the environment it actually has. And the way this works is that we take the system, which in this case is the mechanical resonators, we do weak continuous measurement, we build up a history of its motion, and then we can compute the effective Langevin forces and the dissipation as though the system is embedded in an environment of our choice. Some fake environment, but an environment for which we can create our own non-Markovian correlations. And this here just basically imparts or imposes the fluctuation dissipation theorem. Okay, along with the dissipation, we have to add the appropriate noise. Okay, so this ensures that the fluctuation dissipation theorem is valid. Okay, so is this part clear? Okay, this system, this protocol basically allows us to create any kind of environment we want, not just the one that it is imparted with. Okay?
Environment engineering.
Reservoir engineering, exactly. Okay. So the first experiment we did, and this is exactly what you're talking about, Delatore's predictions, was these were the experiments that we had shown before, which is the Markovian kind of a reservoir, and the red data was the Kibble-Zurek-like protocols that we had extracted. But when we impose a non-Markovian, in this case a sub-ohmic environment, which looks like this, what you see is that the growth of the ordered phase still looks rather universal, but the critical exponents of this phase transition are now different. So here's a phase transition where, or an example of a phase transition where the critical exponents are actually intimately connected with the correlations of the environment. And by changing the correlation of the environment, we can change the critical exponents of the phase transition.
Is that still on the Dekey bond that you talked about?
Yes, exactly. So these are the exponents for the Markovian data that I showed before, and these are the new exponents for the sub-ohmic reservoir.
Now,
Okay.
you can continuously change those exponents?
Exactly.
So the time scale or the correlation
Exactly.
scale of the
Exactly, and we can change the power law as well.
Will you try to super?
Have it?
Super the other way.
Not yet. Yeah, sure. But
That
we could.
actually have more non-Markovian behavior.
I see. Okay. So based on this, what we can see is that the phase diagram remains the same, meaning you still have this disordered phase in the U1 broken symmetry phase, but the critical exponents are very different. Okay? The other aspect of it, which is actually really important, is that there have been a large number of Kibble-Zurek-like experiments, but usually the exponents they extract is the mean field exponents. And why is that? Because the system, by these kinds of Kibble-Zurek protocols, the system in a certain sense goes blind to the critical point while it is still very far away. You're quenching the system, and long before you actually get to the critical point, the system has frozen out. So usually, you're only sensitive to mean field aspects of this of the phase transition or of the critical point. But in a driven dissipative system like the one we have, that is not quite true. And this is kind of a little, kind of it gets it to a little rather arcane, but I'm happy to discuss this offline. But what we actually realized, or what we found out, is that if we now go from this kind of a single scaling universality to a dual scaling universality, where we both scale the observables with the quench rate as well as the temperature, we can actually extract the true nature of the critical point, and we can demonstrate universal scaling behavior. Not let me go back here. As you can see, we can see this universal collapse in the linear regime, which is the mean field regime, but not in the saturated regime or the dynamical steady state here. But by doing this dual scaling, we actually see universal scaling collapse across the entire region. Okay? And this kind of a dual scaling form for the subohmic reservoir is, based on our calculations, is expected to obey this kind of a scaling form, and this is corroborated by our data here. Okay? So I've shown you a case of a non-Markovian or a subohmic environment which preserves the phase diagram but changes the critical exponents. One can also ask the next step of, can we actually come up with an environment or a non-Markovian environment which completely changes the nature of the phase diagram? And that based on our work, we found out that for this decay model, if you have what is known as an Ornstein-Uhlenbeck process, which is this environment with a very discrete coherence time, we can actually see that the system actually has a very different phase diagram. I will, in the interest of time, I'll kind of skip past this, but I will just go to the phase diagram. So this was the phase diagram for the Markovian or the ohmic case. There were just two phases. For this different kind of non-Markovian environment, what we see is that the phase diagram is actually significantly richer, and there is this third phase that shows up, something we call a U1 cross Z2 phase. And this goes beyond Delatore's work, where they basically, their work basically said the phase diagram is retained, but the critical exponents can change. But what we are saying is there are reservoirs you can engineer which actually give you a completely different phase diagram.
This is new. Yeah.
This is new. And this phase is actually very, very interesting. It is what we are calling a continuous breaking of time translation symmetry. So it's a time crystal, but one that breaks continuous time translation, not a discrete time translation symmetry.
But let me just be sure. Earlier you actually showed the Lindblad equation, which is really Markovian
That's
in the
right.
dynamics of the system.
Yes.
But you added what people these days call non-Markovian, but it's actually non-ohmic.
Exactly. And there you cannot write down that kind of master equation.
Right. You have to make it more consistent with each other.
That's right. So it's very much how you describe this theoretically through any kind of master equation like behavior is very much an open problem. We know how
to do it, but you also mentioned that you demanded the fluctuation dissipation relation to be correct. In which case, the dynamics of this open system and the bath should be consistent.
Exactly. Yes. Yes. And there's some very. We have done that, but we can also. I won't talk about it now, but we have also deliberately violated the fluctuation dissipation theorem to see how criticality changes, and that's also very interesting. Though I won't talk about it here. Okay. So just to explain why we're calling this a time crystalline phase, this is actually, I don't have time to go into these details here, but basically remember the model I had described before. The model I had described is I have two modes, a signal and idler, and if I drive the system with a pump frequency beyond a certain amplitude, the signal and idler excitation spontaneously develop a steady state, and they do so by breaking the U1 symmetry. Now, once the U1 symmetry is broken, of course, these signal and idler excitations can gradually meander around. That's just phase diffusion, and there's a Goldstone mode associated with each. But at least in the short time frame, this spontaneously broken phase is constant. As I go into this U1 cross Z2 or time crystalline phase, what happens is that now these two modes, the signal and idler modes, having developed a steady state, now start spontaneously oscillating about each other. And they oscillate about each other at a frequency that has entirely to do with the properties of the non-Markovian bath. that frequency has nothing to do with the signal and rider Hamiltonian, but is entirely given by the properties of the non-Markovian path. Okay? And more importantly, that unlike the time crystal experiments done here by Chris Monroe's group and at Harvard by Misha Lukin's group, this is not just merely a period doubling. This is actually a continuously broken symmetry, because the frequency of oscillation grows smoothly from 0 to a finite value at the same time that the susceptibility of this frequency diverges. So this is actually a continuous phase transition from a stationary state to a state that spontaneously breaks this time translation symmetry. Okay? And we have indeed, and there's some very interesting properties associated with this new kinds of time crystal, among which is the fact that the excitations of this time crystal actually have the same topology as a Mobius strip. And that results in some very robust entanglement even at finite temperatures. If you're interested, I can discuss that in a little more detail offline. Okay, but that's explained in this work here. Okay, so this might seem like theoretical conjecture, but we have indeed verified this in our experiments, showing that this phase indeed breaks this time translation symmetry into this oscillatory phase. And more importantly, and rather this is something that's ongoing work, we have also shown that this phase obeys certain aspects of universal scaling behavior, though right now we are trying to calculate or trying to understand what these scaling exponents are. These are the exponents we measure, and we are trying to understand how to kind of understand or how to predict or explain these exponents here. Okay.
How does it change when you go from ohmic to sub-ohmic at that point where this phase begins to appear?
No, this phase does not appear. This phase does not appear when you go from ohmic to sub-ohmic. It goes from this phase appears when you go from ohmic to an Ornstein-Uhlenbeck process. So that is rather important. Let me just go back here. So this phase appears, the Ornstein-Uhlenbeck kind of a reservoir is associated with one discrete reservoir coherence time, tau r. So it's this, let's go back here. It's this time scale. Okay? And what the phase diagram I'm showing basically involves gradually, you can think of the Markovian limit of this as just tau r going to 0. And this phase appears when we reduce tau r. And that's at very, very long coherence times of the environment is when this phase appears. Okay.
So it's not just a ohmic sub-ohmic?
No, it's not. Ohmic to sub-ohmic preserves the phase diagram, but the critical exponents gradually change. But ohmic to Ornstein-Uhlenbeck, beyond a certain memory of the coherence time of the environment, this new phase appears. Yeah. Okay. And these are ongoing experiments where we are actually building arrays of these kinds of, or a lattice of these kinds of resonators. And to show that, and I won't go through this in too much detail, but this, while we have demonstrated this kind of a time crystalline phase for a single cell experiment or a system without spatial extent, what we also have shown is that this phase is indeed robust or has robust long-range order because of optomechanical synchronization. Okay? I won't, and this is just some of our simulations of how this long-range order of this time crystalline phase is actually established. And this time crystalline phase, like I said, has two broken symmetries. One is the U1 symmetry of the angle, but the other is a discrete symmetry which corresponds to the oscillation period of this time crystalline phase. And you can see that after following some coarsening behavior, there is indeed robust long-range order. And this long-range order comes about because of optomechanical synchronization. Okay, so with that, I'll kind of conclude. What I've basically shown you through both our cold atom experiments and our optomechanical experiments is that open quantum systems, or the regimes where intrinsic interactions and dissipation kind of commensurately have a commensurate interplay, is not just a crossover or a flyover state where you go from coherent quantum behavior to classical behavior. There's actually a lot of very new physics that can appear in this intermediate regime. And one of the things I've shown, which is a past prediction, is that when you engineer or when you create reservoirs that go beyond the ohmic or beyond the Markovian regime, the nature of the nature of driven dissipative transitions and the nature of criticality can indeed morph. You can get different kinds of critical exponents with different kinds of universal behavior. And there are certain kinds of environments, for instance, this Ornstein-Uhlenbeck kind of an environment where not only are the critical exponents modified, the entire nature of the phase diagram itself is modified, in particular, in this case, leading to some rather novel dynamical steady states, such as a state with continuously broken time translation symmetry, or a time crystalline state. And we have shown that this time crystalline state is indeed robust and does indeed exhibit universal scaling behavior, although right now we don't entirely understand the scaling or the critical exponents of this transition, and that is ongoing work. But we also want to extend this deep into the quantum regime and ideally study the quantum critical properties of these kinds of emergent phases. And the work I described is kind of a few drafts circulating around, but hopefully we get to write this up soon. This is just part of we have 3 labs right now, and the experiments I talked about are in this optomechanical system lab, but we also have other laboratories in our group studying various kinds of non-equilibrium behavior in ultra-cold gases, optical lattices, and that's based on our work on optomechanics, which was actually initially motivated by metrology. We have ongoing experiments where we are actually shockingly trying to do something useful to try and use these optomechanical systems for various kinds of material studies and so on. And with that, I'll thank my group, in particular the graduate students responsible for the work I talked about, Yogesh Patil and Harry Chung, and some really amazing undergraduates. Laura Chang is recently graduated. She's now a graduate student at Princeton. Earlier contributed a lot to the silicon nitride work. She's now a graduate student with Martin Zwierlein at MIT. And Ivailo is now a graduate student at Caltech with Manuel Endres. So we're kind of trying to keep it in the AMO family. With that, I'll thank you very much. Thank you for your attention.